Good afternoon. I welcome you to my presentation about generating individual AI accelerator. That's a project that's currently, we are currently working on at the ZHAW, the Institute of Embedded System. My name is Thierry Delafontaine, and I work there for now about 3 years. So, what is it really about? So basically, we have a neural network, and we have some FPGA, and what we want is to create an accelerator for our neural network that fits our resources. However, we want to minimize a certain cost function or a certain number of cost functions. And to go a little bit more into detail, what we actually do, just some background. What are FPGAs? I suppose most of you know what an FPGA is, but still that you know what their advantages are. So here we have a picture of a normal CPU. You see we have some cores, and the cores are big and have a lot of functionality. Now, when you have a sequence of tasks, we need to kind of read the instruction, then get the data from the memory, then we execute the instruction and can finally put the data back to memory. And this we do basically for each task. So when the tasks are dependent on each other, we cannot really parallelize that. And that's what makes CPUs in that regard not that efficient. And this we do for every task. So then task 2 and then task 3 and so on. Now, FPGAs work a little bit differently. So on the right side, you see the FPGA. On the left side, still the CPU. FPGAs have a lot more basic cores, but they are a lot more limited in terms of what they do. So what we can program then inside the FPGA is what this small core does and the interconnection between them. And what we can do now is basically not like on the CPU where we have to go back to memory. We can go from one core to the next one and to the next one to the next one. And this is called stream processing. And that is kind of really what FPGAs are really good at. And it is similar in the world of accelerators. So we have kind of two types of accelerator for AI. One type is the traditional one, which you see a lot as a coprocessor, and the other style is the data flow style accelerator. And to show you the difference between them, we will assume that we have a network, or no, it's not really a network, it's a sequence of layers that looks similar to this. So we have a convolution, then a ReLU activation, another convolution, again a ReLU activation, then max pooling and batch normalization. For those of you that are not, that doesn't know neural networks a lot and don't know what these layers do, just know that basically for each layer we have a matrix of data. We get as input, we do some operation inside the layer, and we get another data matrix as output, and that we feed into the next layer. And what we want to accelerate is basically one layer of those, and then the next one, and then the next one. So here you see a traditional accelerator. That's the one which NVIDIA uses in their newest Jetson devices. You can look it up on the source. It's called NVIDIA Deep Learning Accelerator. And I will explain you the components in the example. So first we want to accelerate the convolution, and for that the accelerator has a convolution core. So we accelerate the convolution there, and as next we try to accelerate the activation function, and for that we also have an activation engine which is specifically built for that. And here you see that also this accelerator does have a kind of data flow style, so we don't have to go back after the convolution to the memory in order to also accelerate the activation. So we can directly go from the convolution accelerator to the activation accelerator. And then in the next step, where we want to accelerate the convolution, we have to go first back to memory, because there is no way we can go back directly to the convolution accelerator. And here you see one key point of these traditional accelerators. So even though convolution 1 and convolution 2 are the same operations, they're not really the same when we want to parallelize them. So the input sizes are different, the kernel sizes are different, stride may be different, and also then the output is different. So this convolution core needs to be that flexible that it can accelerate a lot or a wide variety of convolutional layers. When we proceed with our example, we can accelerate the activation, the max pooling, and the batch normalization all in one go. And here you see another key component. In traditional accelerators, they usually target like really known sequences, and this sequence is really known. So in CNNs, you probably have seen that we have convolution, activation, max pooling, and batch normalization. Now, how would we accelerate that on an FPGA? And on FPGA, we don't need to be flexible in that case that we have to accelerate a lot of different layers, because basically when we get another network, we can reprogram our accelerator. So in our case, the best solution would be to generate an acceleration for each of the layers and kind of have them in sequence after each other. But usually this is not a really good solution, or it is not very feasible, because the resource usage is simply too high. And the most restricting resources are memory and multipliers. And just to put that into context, maybe you saw it also in the early presentation this morning. On the left side, you see you have a mobile net. That's a really small network in the CNN world that takes a 224 by 224 image and has approximately 81 layers. On the right side, you see an FPGA, the Vertex 7, and that's the biggest one in terms of DSP slices. And there's another one which is a little bit bigger in terms of the block RAM size. And you can, when you compare the numbers, you can see that it is not possible to kind of have a one-to-one mapping of all the operations. So 325 million multiply accumulates compared to 3,600 DSP slices. So one slice has one multiplier that multiplies an 18-bit times a 24-bit signed number. Equally the parameters, so these are all the weights. We have 2.6 million weights and only 52,920 kilobits. And what can we do to still get a reasonable solution? And I see those two solutions as kind of part of a design space. So here you see the blue line is kind of the optimal designs, and a really bad design would be on the top left corner. And if you would kind of have really good solutions, then we would get this line. And on the left side, you see this layer by layer accelerator that we saw earlier, the traditional one. And on the right side, a data flow style accelerator which accelerates each layer independently. And what we kind of want to do is basically draw a line where our FPGA has our resource limit, and at the intersection, we basically get an optimal accelerator with optimal performance. And we do that by have a mix and match between those two worlds. So some layers are accelerated on one engine in a group, and the others are accelerated individually depending on how resource hungry they are. Now, what is really about, and I want to tell you that with this chart, with our where you see our framework. And the central component here is the factory. So basically the factory takes in all the necessary information and produces the final output. And the output in our case is directory where you have the HDL source output. So basically we output VHDL or Verilog, which makes it independent to your synthesizer use or the tool chain. Yeah. On the left side, you see our inputs. So basically we have a resource definition we give to the framework that says, hey, we have that many DSPs, that many block RAM, and so on. And also a neural network definition. In our case, we use ONNX, just simply because ONNX is very known in the field of embedded neural network acceleration, and has a very clear standard which operation are supported and how they work. And that leaves also kind of all the quantization and training process up to you, so you can use whatever framework you want. Then we have the two components which give us our solution, and basically this is the component library, which you will see here with the component interface on the top, on the lower right part. And these are the kind of code snippets which accelerate each individual layer. They are parameterizable with parameters, so kind of the parallelization and so on is parameterizable. Then on the upper right part, we have the optimizers, which are our design space search algorithms that actually find or propose us new parameters to get better solutions. And here you see we have only interfaces defined, and the reason for that is that we want our framework to be extensible. So usually for a problem or for multiple problems, there's not one golden solution. So one solution might work for one problem and another solution might work for another. That's why we have only interfaces defined and basically can add multiple different solutions. On the lower part, you see that we have different operators. And if you know ONNX a little bit, ONNX defines a neural network as a graph with different operators. And for each operator, we need an implementation. But also within this operator, we need to have, or we can have different implementations. So for example, if we want to accelerate the convolution and our goal is throughput, we can have an implementation that increases or throughput as most as possible, but uses DSPs, for example. And there might be another solution that doesn't use any DSPs, but it's a little bit slower. And with that, we can play in the optimizer. And then on the upper part, you also see that we can have different optimizer implementation just to get different solutions. Another key component of our framework is usability. And when I want to make something usable, then I look and see what other great frameworks do. And I took inspiration from Keras. And those of you that did something already in Keras with AI know this workflow. For the others of you, I just go quickly through the workflow, which I find is really simple, but still gives you the freedom to kind of inject your own code and do custom stuff. So basically on the top, you see that we define a model with keras.sequential. Then we compile our model, which is more a configuration of our fitting. So we give basically our loss function, the optimizer we want to use, and can also give certain metrics we want to track. Then we call the actual fit function with our training set and define some fitting parameters like batch size, validation, and of course the epochs, how long we want or how many iterations we want to train on. And then we can also insert custom functionality with the callbacks. So in this case, we could maybe kind of return the metrics we configured before. We can give them to TensorBoard and we can display them, for example. So our problem is really similar, but not really the same. And in our case, we define, instead of a model, we define an accelerator. And we do that by giving it the ONNX model. And then we can also compile or configure our fitting process. And here, instead of loss functions, we give the compile method the cost functions, what we want to optimize. So for example, we want to optimize throughput, want to minimize power consumption. And because we can give multiple cost functions, we must also weight them. And then we can also define an optimizer and can define other metrics which we want to track, for example, BRM usage and how many DSP slices we require. Then we also call the fitting function. In our case, we don't fit weights to certain training data, but more we fit our accelerator onto the hardware resources. That's why we give in the resources, and then also a number, how many iterations we want to let the fitting process run, and then we can also add custom callbacks. Now we are at the stage that we have a fitted network, fitted accelerator, and we still want to export it that we can synthesize the material. So we call this export function, and we can give an output path, basically the directory where all the files are put into, and the top level language. So in the current stage, the top level language can be the VHDL or Verilog, and that's for the top level entities. And the components themselves are exported in the language they are written in, so either Verilog or VHDL. But most synthesizer programs, so at least the ones I know from Quartus or Xilinx, support both HDL languages. Then what is the current state? So this framework is still in development. The state is that we want to have a proof of concept end of June, so we will have only a minimal amount of operators that we support and only a minimal amount of optimizers to kind of have the whole workflow ready. But there are plans. This is the part where we are currently working on, so basically the optimizer implementation and the output part. Next, or how do we want to proceed with this framework? So basically first we want to increase the amount of operators we support, because the more networks we can support, the wider this framework can be used. Equally with the optimizers, and I think that's something that's a point we can learn a lot, because for us it is kind of a new field, this design exploration, and there we can gain a lot of knowledge by implementing different optimizers and see which ones perform better in certain circumstances. And then another kind of goal that is a little bit more far ahead. So maybe we will add ONNX runtime support. And for those of you that don't know ONNX runtime, so ONNX runtime is a runtime that takes your ONNX network, and you as an acceleration provider can say, hey, I have an accelerator that can accelerate these and these and these operations, or this selection or sequence of operations, and the ONNX runtime does the scheduling and actually gives you the data and gets it back. And I see a use case for ONNX runtime. So here you have the network or the sequence of layers we previously used as an example. I just added the flattened, dense, and softmax layer on the right side. And we talked about that FPGAs are really strong in stream processing, and dense layers are kind of really the opposite of stream processing. So basically for each output pixel you need the whole input frame or input feature map, and this would take a lot of resources on an FPGA. And here it maybe makes sense to say, hey, we accelerate all the other stuff which can be good implemented on the FPGA and output the data of the batch normalization, and OneNX runtime takes that data and then accelerates the rest of the layers on different hardware. So that could be CPU or GPU or whatever your device supports. So now I am at the end of the presentation. I hope you got an insight of what we do at the INES and what this framework is about and at which direction we're going. And now I will be available for questions. And thank you a lot for listening. Any questions? Yeah. So we will potentially use it in-house, but there's actually not like an industrial customer that we kind of sell the or kind of do that for. Currently, it's a master thesis in-house. So, yeah. Other questions? Yeah, so maybe for those of you interested in the topic, this is a framework done by Xilinx, which kind of goes into similar direction. They also, maybe those of you that were in the presentation of Robin Müller this morning heard about Vitis AI, and the difference between Vitis AI and Fin is the same difference we saw earlier between the traditional accelerator and the data flow style accelerator. So Vitis AI works kind of in this loop where we accelerate layer by layer, and Fin is more a data flow style accelerator. So basically you instantiate multiple DPUs and kind of want to create this data flow style, which you see in which you see here. So you loop data through multiple accelerator. And if someone is really interested in this, yeah, go on their GitHub page. And they have a lot of resources actually about this topic. Maybe someone wants to add something? No? Then I thank you for being here and for listening, and I hope I could give you a good impression of what we do. Thank you.